So start with the limiting reagent again, and stoichiometry. Let me just open this workbook for you. Oh, wow. Okay, let me just bring one thing. Okay. Okay, let's quickly revising that what we're up to from chapter 1 and 2. So, well, we are learning about quantitative. You don't have to copy this down. I'm just giving you some big bit of like summary that we're very learning. So we are still doing the quantitative chemistry, and we started learning about something known as moles. Okay, mole is basically, we define it as the kind of packaging unit. It's a really big packaging unit, which is the Avogadro's number of the 6.022 times 10 to the power 23. So you've been having a lot of questions about asking you, hey, we have a number of moles, how many molecules, how many atoms of that. We also learn about like some of the difference between empirical and molecular formulas. Again, empirical formula means that the simplest ratio forms of the compounds you have, whereas molecular formula is like the full the numbers of the atoms in the compounds. So kind of describe that as empirical, more like an initial or like a nickname, like an initial of your name. Molecular is kind of full name of the whole thing. Okay. And then we're also learning about this, that N is equals to mass over molar mass last time. Okay, that if you're given a certain mole, but think about the limitation given over here. When we say that N equals to M over molar mass, this is only limited to the solid states. That you are most likely given a certain amount in grams, and then from the grams you're able to find how many moles you can have. Today we're going to learn about kind of different things. We got a new finding number mole method that's N equals to CV, but let's explain that a bit later on too. Yes, of course, after that we learned that we kind of practice limiting the reagent. I uploaded some summary of the limiting reagent video, so if you're not too sure how to deal with the limiting reagents, make sure you watch that. This is relatively, compared to my other videos, it's relatively short, only about 10 or 15 minutes, giving you all the templates and guidelines to deal with the limiting reagents. As I said, I gave you like more detail, like all the working out. You probably don't need to write all that in details, but still recommend you to write all the details until you get feel familiar or like confident you're dealing with the limiting reagent questions. And then later on, you can just see like by just looking at the your reactants, you'll probably be able to see like, oh, that's a limiting reagent straight away. Okay, and that's what the skills that you need for year 12 later on. So today we're going to talk about the concentration and molarity. So and this uses a bit of like the solution chemistry that we learned in year 10. So when we say the solution, we believe that we have a solute that's mixed with the solvent and producing the solutions. Now, in terms of state, solutes is generally be solid or could be the gas, depends on what you prepared. Sometimes a liquid. Okay, really depends what you put it in. Solvent, however, is generally we're using a water as a solvent, as comes in liquid state, and aqueous for the solution forms. Yes, it sounds like, yeah, okay, it's kind of theoretical. I'll show you what that means by solution chemistry and really the examples. This is the vitamin C tablet, if you have ever tried it before too, okay? So when I say solute, I'm simply meaning that I'm putting one tablet into the jar, okay? Now, this is a solute, as you can see, like it contains a bit of like some certain amount of vitamin C, maybe some sugar. When I put some water there, as this is a highly soluble, and leave that, let me feel like about quarter, you start seeing that it's getting dissolved, making a solution there. So let's have a think about like in terms of here. If I drink everything, then it's equivalent to like I'm taking the one tablet as well too. But the reason why I'm making the solution is it's easy to drink, easy to consume too. So this is now a solution of the vitamin C, or like the Veroca solution there. Okay, so give a more stir, fasting up the reaction. And as you can hear the fizzy sound, the CO2 is coming out. So you can think about like, you can imagine about what kind of chemical reactions are ongoing in here. So this is basically the solution chemistry that we're going to deal in all chemistry in year 11 and 12. Solute, like in a vitamin C tablet, put it into the water, the solvent, which is dissolved in that, making the solution forms too. Pretty simple, okay? But when we're talking about in terms of their concentrations, this is something that's very important coming out. So generally, when we say the concentration of the solution, we kind of define that as it depends on the amount of the solute that you put it in, and on that the volume of that solution that you have. This is how we define the concentration. So, for example, for that Veroca or like vitamin C tablet, this solution given here, I would say that's about. For example, that's about, I have a one tablet on that, maybe assume that that's 100 mils, given here like this. The way we can interpret that is, if I drink the 100 mils of this solution, then I'm taking, it's equivalent to I'm taking one tablet as well too. Does that make sense? Okay, it's pretty easy. But if I increase from here, see that this is the amount of the water, the solution that I have. If I add a bit of like a water in there, make it a half fill, that, okay? So as you can see, like from the colors of the solution there, it was kind of dark yellow or orange yellow. Now it's a little more pale or kind of diluted. But if I drink the whole thing, it's gonna be hard, but if I drink the whole thing, I'm still taking the same amount of a tablet, which is 1. So this is called a dilution, that we're adding extra water or increasing the volume, maybe like decrease the concentration of that. But in terms of the amount of the you're consuming by drinking that 2 different solutions, you're still getting the 1 tablet as well. Okay, so this is a basic. There's actually an A to Z of the whole solution chemistry. That's something that we have to understand. So page 72 of your workbook, it shows you that some example of the concentration of the 2. Give you some summary. So when we put the some little bit of salt, like if then we believe that it's kind of diluted. Means that it simply means diluted solutions. I can write it down in there too. Diluted solution. It's either be the less the solute, you put it into the solutions. So instead of having the 1 tablet, if I put the half, that's a diluted because I don't have many. I don't have much of the tablets inside. Or the high volume. There are 2 methods that we can describe diluted solution. So for example, that half-filled bottle is now diluted compared to the quarter-filled. Concentrated solutions, concentrated solution is kind of described that as we have the greater amount of the solute and the low in terms of volume. So for example, if I just kind of dehydrate all the water, like let's say I keep some heat, evaporate all the waters out, then you would see that really concentrated. Like you can think about the concentrated cordial. Okay, has anyone tried just the cordial itself? Yeah, okay, if you haven't tried that, you probably know what I'm talking about. It's a super sugary that, even for a small amount, with a teaspoon of that. So we don't really drink the cordial by itself because it's too concentrated. But what we do is we put like a certain amount of water until you feel like finding your best taste. And that's how we make it from the concentrated solution to the diluted solution. So we call that as dilution process. But simply, have a think about in there. The most important thing about those during the dilution process that we're going to discuss later on is even though you drink a small teaspoon of the cordial or a liter of the cordial which is diluted, you still get the same amount of sugar. Because we don't really change the amount in here. So the amount of the solid will remain the same. Just like this half-filled bottle of that's vitamin C tablet and the quarter fill as well. Does that make sense? Okay. So we have a few methods to show that, a few units representing the concentration, which is given on your page 73. We have a various unit of the concentration. There are really usually a lot. And we kind of use that in everyday life a lot too. So started from the gram per liter. It means that we have a 13 grams per liter. We can have the parts per million. Okay, milligram per kilogram is given as that. Write it down as, this is also same as milligrams per liter too. So let's have a talk about a bit of a unit conversion, so probably if you're not so familiar with. So when we set the grams over here, okay, for the smaller unit, we can go for like a milligrams. We can go for like a microgram. So that's a micro, that's a milli, that's simply a unit. We can even go for the nanograms, ng, that's a nano. For the bigger side of that, we can have gram to a kilo, kg, kilogram. We can have the M, capital mg, that's a mega. We can also have the capital GNG, that's a giga. And the rule is pretty simple. From one unit to the moving to the down, you simply, because we are moving from the bigger to small, that's going in times that 10 to the power of 3. So for example, 1 gram is equivalent to 10 to the power of the 3 milligrams. Does that make sense? Okay, that's pretty simple unit conversions. From milligram to micrograms, okay, that is not the m, that's a mu. So mu is drawn as big tail and small of that. That's a symbol of the mu, that's a micro. From that, we also get times 10 to the power of 3. And goes like 10 times 10 to the power 3, like this, from micro to the nano. Which means 10 to the power 3 milligrams is equivalent to 10 to the power 3 times 10 to the power 3 micrograms, which is what? 10 to the power 6 micrograms like this. And this is equivalent to 10 to the power 9 nanograms, goes in that order. Now, if you want to convert it from the small to the big unit, it's got to be moving this direction. You can either divide the 1,000, or the simplest method is using the power of the 10 times 10 to the power of the minus 3. And then same method, going back minus 3 and times 10 to the minus 3. So for example, 1 milligram is equivalent to 10 to the power of the minus 3 grams. You probably learned that in year 9, year 10, and the mathematics and unit conversion sessions too. In chemistry, we use various units of the gram, various units of the liters, volume. So it is very important that you need to know how to convert the unit effectively. Grams to kilogram is same methods. From kilogram to gram, it'll be 10 times 10 to the power 3. Mega, it'll be times 10 to the power 3 again. Giga, times 10 to the power 3. But going in this order, is always times 10 to the power minus 3. It's not only for the grams, by the way. We can use for any of the units. Like for example, liter to the milliliter, to the microliter, to the nanoliter. Liter to the kiloliters, and microliters, megaliters too. But we generally stick onto liters because liters is a kind of standard unit we use, and we don't really get much of the megaliters, to be honest, practically. So one thing that you also need to remember is the water density, the density of the water. That is, if you have a 1 gram of the water, 1 gram of the water, is equivalent to 1 milliliter. So what we write that as 1 gram per milliliter, which is same as 1 kilogram of the water is equivalent to 1 liter as well too. So if you have a 1 liter of the water, that's equivalent to the 1 kilo. That's the water density that we use, quite common in solution chemistry. And we believe that all the other solutions would have the similar densities unless you're given the different values. Okay, now let's going back to the units again. We have a parts per million, that's a ppm in short, has the milligram per kilogram, which is same as milligram per liter. So in other words, if you want to change to grams, that would be equivalent to 10 to the power minus 3 grams per liter. Okay, and it is very important to leaving your unit to the grams later on because we may need to change to number moles too. Okay, remember that number mole, or using the N equals to M over molar mass. For that M, we have a gram of the standard unit. Okay, so later on you learned about more of the unit conversions. Milligrams per liter, so mg per liter, pretty easy. Parts per billion is something even smaller than the parts per million. That is same as microgram per liter or micrograms per kilograms too. Again, microgram means what? 10 to the power of the minus 6 grams per liter. Now, we have all the other percentages too. We have 3 percentages. We have a percentage by mass, percentage by volume, percentage by mass per volume. So, it is very important that you leave the percentage in the specific the contents you have in the given solution too. Now, a good example of percentage by volume is, if you think about this kind of hand sanitizer, you may be able to calculate how much of the alcohol is contained in that in terms of percentage. That would be volume per volume because we have a volume of this solution form inside. Another good example is the alcohol beverages. You may see like alcohol content would be 6%, 10%, 20%, like depends on what kind of alcohol beverages you have. That would contain in the volume per volume percentage of the two. So let's go in more details about by doing some questions here. So question 3.1, what is the concentration in gram per liter of the solution containing 8 grams of sodium chloride in 500 mils of that solution? So let's write it down, the working out for this, 3.1. So to find the concentration, we use the unit C. That's a symbol of the concentration, obviously. Then for the sodium chloride, we can write it like this. That's how we can represent the concentration of the sodium chloride in the symbols. You're given that 8 grams. So what we're going to put is, always remember that we have a solute on the solvent or the solution volume. Solute amount on the solution volume. So in terms of the solute you're given 8.00 grams on the top. So yes, try to put the units in your substitution too. We have a 500 mils, which is 500 milliliters given. I just wrote it down what you're given. Then look at the question that what units you have to convert it into. You need to convert that into grams per liter. Which means I don't need to do anything with the 8. This is the same grams, so 8.00 grams given. But from the milliliter to the liters, okay, the simple thing is from the small unit to the big unit. So what do you need to do? 500 times 10 to the power minus 3. Use the unit conversion again. Or if you just think that, 500 mil is the same as 0.5 liter, that's fine. That's fine. But just make that as a practice too, especially in the exam period, exam like in the conditions too, because you may sometimes get confused about unit conversions. Okay, if you're not like 100% awake or something, then I recommend using this. This is a chance, like no chance making any mistakes by doing so. Then you simply put it in your calculator. That'll be 800 divided by 0.5. So sorry, 8 divided by 0.5, which is 16 grams. And the given fix of the 3, 16.0 grams per liter then. 500 itself is actually like a 1 fix, so you might just say 20, but just leave that for 360 for now. All right, let's do one more. The next pages, there are a few more there. Let me try yourself. What is the concentration in grams per liter of the solution containing 5 grams of glucose in 250 mils of the solution too? So same procedure basically. Concentration of glucose can be found by amount of solute. So you're given what? 5 grams. So 5.00 grams of the solute divided by 250 mils. This again can be converted into the 5.00 grams divided by 250 times 10 to the power minus 3 liter like this, which is 5 divided by same as 0.25 times 4, which is 1.25 grams per liter then. Oh, sorry, 5 divided by, not the 1.25, 5 divided by 0.25, not the times, yeah, 20 grams per liter is the right answer then. 3. A saturated solution of the calcium carbonate was found to contain 0.0198 grams of calcium carbonate dissolved in 2,000 grams of the solutions. Calculate the concentration of the calcium carbonate in the solution in the parts per million. Okay, let's start writing down all the given information you're given. So, to find the concentration of the calcium carbonate, CaCO3, you're given that 0.0198 grams, that divided by given amount of the 2,000 grams of solution, so 2,000 grams underneath there. Okay, now if you remember the ppm, ppm is same as parts per million. That's a milligrams per kilograms or milligrams per liter. Depends on what kind of solution mass given or the volumes given. So it's simply then unit conversion. You change the grams into the milligrams in your numerator, grams into kilograms in your denominator then. So think about it here. We have grams to change the gram to milligrams, big unit to small unit. So 0.0198, that times that 10 to the power of the 3. Okay, and then if you want to change the grams to kilograms, you times that 10 to the power of the minus 3. Does that make sense? That's a 2,000. And simply put that in your calculator. Okay, that is 0.0198 times 10 to the power minus 3 divided by 2,000 and 10 to the power of the minus 3. You must get 9.9 milligrams per kilograms, which is what? Same as 9.9 ppm. Then we can write that in the unit of the ppm then. So ppm sounds really confused because we have a unit of the milligrams and kilograms too. And we kind of use the ppm to measure the amount of the air, like dust in the air, atmosphere, or amount of these like a microfiber, like metals, stuff like that too. So you gotta see like the ppm quite a lot in year 12 and in the year 11 as well too. All right, next one. A sample of the tap water found to contain 0.0537 grams of sodium chloride per 250 grams of solution. Calculate the concentration of NaCl in the ppm again too. So let's share that. We have a sodium chloride here again. You're given that 0.0537 grams of the sodium chloride per 250 grams of the solution that you have given. Again, unit conversion from grams to the milligram, grams to the kilograms. That's all you need to do. And then what you need to realize from grams to milligram, it'll be 10 to the power of the 3. Grams to kilogram, that'll be times 10 to the power of the minus 3 like this. Then just put that 0.0537 and 250 there. That's it. And just put it in your calculator. Then you should get 214.8. Now, fix that into given sig figs values. You're given 3 and 4 sig figs. So you're dividing 3 sig figs divided by 4 sig figs. Follow the lowest sig fig values you have. So to fix that into 3 sig fig, which is the lowest, that is 215 ppm in 3 sig fig. Okay, It's not that complicated if you knew if you know how to convert the units correctly too. Sometimes, as I said, not only for the grams, liters can deal with the same, especially milliliters and liters forms. So I would like you to try those try yourself questions that you have on your up to page 78. I'll give you about 10 minutes. Let's see how it goes. you marking this one now?
Yeah, do you want me to mark these ones first?
No, this is urgent. I need to keep them back. So when you finish marking this, the module 2 test, can you bring it into the room? So I need to put it on. I need to keep them back. Thank you. Okay, let's have a look at those try yourself questions now. One, a 750 ml bottle of the whiskey contains 244 ml of the ethanol. What is the concentration of the ethanol in percentage? So, to find the percentage or the concentration of your ethanol, the way we can find the percentage is you put that volume of the ethanol, 244 milliliter, on 750 milliliter. Now, for the volume per volume or the percentage, it is very important that you're matching the unit on the top and bottom, and then simply times 100% of that. This is how you can find the percentage. That will give you that 32.5%. And at the end of your unit, guys, this is something that's very important. The question asks you specifically about volume to volume. Follow the unit. That is volume for volume. If you just ended up writing a percentage there, I don't know whether that's a percentage by weight per volume, weight per weight, volume per volume. So it is very important to write it down volume for volume. Okay, easy mark, but you can lose a mark because of this too. 2, the concentration of ethanol is 350 mils. Bottle of the beer is 4.9%. Calculate the volume of your ethanol in the bottle. So to do so, if the percentage is given as is 4.9%, I should write it down like this, of the ethanol is 4.9%. Remember that this is found by solute or solution times 100% like this. So simply the way we can find it is from the total volume to find the amount of the solute can be calculated by percentage, 4.9%. Times that to the given the total volume of the solution that you have, 350, or just use a common sense or like mathematical concepts. Then you get 350 times 4.9% means 4.9 and divided by 102 times 350. So 350 times 4.9 divided by that, you get 17.15. Given that fixed unit to the sig fig of 2, this is 17%, 17 milliliter there. Easy. Next one. Calculate the concentration of the following solution in ppm. So we have 25 milligrams of the calcium chloride, first of all, and we have A, and dissolve the 5 kilos. So concentration of calcium chloride can be found as we have a 25 milligrams on the 5.0 kg. See the unit? Milligrams per kilogram. This is already showing the ppm. So simply put that into 25 divided by 5. You get 5.0 ppm then. Easy. B, we have the lead to nitrate. So concentration of lead nitrate, NO3, N2. That's giving us 1.25 grams dissolved into 2,000 grams. So write it down, 1.25 grams in 2,000 grams, like this. Unit conversion again to grams to milligrams, 1.25 times 10 to the power of the 3 milligrams. That divided by 2,000 grams into kg. That's, you can just write it at 2 kilograms if you like to, the same. Okay? Then you should get 625 ppm. Lastly, C, 4 times 10 to the power of 3 grams of the magnesium sulfate. So concentration of magnesium sulfate is that we're given 4.0 times 10 to the power of the minus 3 grams. That divided by 150 grams of the solution. That's what you're given. Again, simple unit conversion from grams to milligram, but if you see the 10 to the power minus 3 grams, this is kind of showing you that milligrams units too. Or you can just do it like this. If you're not too sure, always bring that 10 to the power 3 and milligrams. You see that? This we cancel out. And that divided by 150 grams into kilograms. That's a times the bigger unit, 10 to the power minus 3, like this. Then your answer must be then 27 ppm. Next one. The nutrition panel of the flavored milk drink states that, this is something that's very interesting. It might be the truth, by the way, for this one. We have flavored milk states that it contains 35 grams of sugar and 7.5 grams of fat in every 250 ml serving. What are the concentration of sugar and the fat expressed in the weight per volume percentage there? So for the concentration of sugar, you can find it as from what you're given the 35 grams. That divided by the 250 milliliters. Okay, now the grams is matching to the milliliters. This is why we need to learn about the water density. Remember that 1 milliliter is equivalent to 1 gram. 1 liter is equivalent to 1 kilogram. So if you have grams and milliliters, we believe that they are matching units, so that you can just times 100% there. Then as a result of that, you should get, did you get 14.0%? And weight for volume. Make sense? Good? Okay, so it's quite a high percentage of sugar in per, like in the flavored milk, maybe chocolate milk, I guess. Concentration of fat, in the same manner too, we have to give in 7.5 grams divided by 250 milliliter, that times 100%. Then you'll get 3.0%. Make sure you put the weight for volume in the final percentage values too. Next one. Ciguatoxin is a dangerous toxin that is found in some fish in the Australian tropical waters. The amount of this chemical that can kill a 70-kilo human is approximately 50 milligram. What is the lethal concentration of the toxin in the human body in parts per billion? So let's start from the concentration of ciguatoxin in like a lethal, like it can kill one person in 70 kilo levels. So that's known as 450 milligrams. So 50 milligrams for the 70 kilogram per person you can kill. So that's given as a unit here. Now parts per billion is, if you remember that, that's micrograms on kilogram. In other words, you need to convert the unit from milligrams to microgram by times 10 to the power of the, from big unit, small unit, it's not a minus, it should be 10 to the power of 3. Okay, at the bottom we have a 70 given as that too. So simply put that in your calculator, you'd get 2.1 times 10 to the power of the 2 ppb, the parts per billion then, in 2 sig fig values. I know 70 is it's actually 1 sig fig, so you may just relieve that to 2 times 10 to the power of 2 ppb, following that sig figs you're given. Next one, fluorine is added to the toothpaste in the form of the sodium fluoride, NaF. The permissible level of the fluorine in the toothpaste is 0.22% of the weight per weight. 175 grams of toothpaste tube contains 0.42 grams of fluorine. Calculate the fluorine concentration in percentage to see if this above or below. So you're given that 0.24, so concentration of the fluorine that you're given is, how much you were given? 0.42 and 42 grams, and given the 175 grams of the toothpaste. Let's just check. Okay, to find the gram in the percentage times the 100%. Then you should get 0.24% in weight per weight. Yep. Okay. Now, question asking you whether this is permissible or not. The permissible level is 0.22%. So make sure you're sure that this is greater than 0.22%, which is weight per weight. Therefore, it's a bit okay. It's above the permissible, the level. Make sure you write down the conclusion as well, though, because that's what the question is asking you. Okay. Any questions about like a converting unit, changing unit to the concentration? Pretty easy. I feel like I'm dealing with like year 9 and 10 mathematics, to be honest. But probably the new thing is the ppm, ppb, that we don't really deal a lot. But it's simply just need to remember that milligrams per kilogram, so micrograms to the kilograms again. So let's now start about the real chemistry. This is just general like a concentration, general like we use in everyday life. When we're talking about concentration in chemistry, as we learned that we are dealing with something really, really small, like atoms and molecules. So again, we're using number of moles. When we have a number of moles in your concentrations and we have the same volumes there, we call that as, this is known as molar concentration. Please highlight that. Very special type of concentration unit, the molar concentrations. This is a unit of the mole per liter. Mole per liter. So remember the mole per liter is also can be written as capital M, like this. In some old textbooks, you probably see the capital M instead of mole per liter. Now, mole per liter is kind of more recent change. Like, it's been like 10 years now, or like almost getting 10 years, maybe more. Capital M is a kind of old-fashioned way we're writing the mole per liter, the unit. Some school teachers, some university, like still using that capital M. So if you see that, just deal that as M as mole per liter. Okay, now this is also known as the molarity. Molarity of the solutions, in short. Or same as molar concentration. And the way we can find the molarity on the mole per liter is pretty same as like what we have done before too. So for example, question 1, let's find the molar concentration of that solution that we contain potassium nitrate. So question 1. Now, the special thing about molar concentration is we're using a different symbol. Yes, we use this C to represent this is a concentration of the potassium nitrate. This is like a general symbol of the concentration. So that C is kind of more like a universal that we can use for any of those units we learned, whether that's a gram per liter, milligrams per liter, whatever, okay? But in terms of for the molar solubility or molarities, we're using the big bracket. This is a symbol of the molar solubility, or like a representations of that. So when I'm writing this, when I'm writing that big bracket and KNO3, this is asking you, hey, find me the molar solubility, not just any concentrations. That means this can be written as, I can rewrite that as N over V here like that. That N, we have the 0.105 mole. At the bottom, we have the 200 mils. Now, we don't accept the milliliter as a standard unit for the mole per liter, so we need to convert that into the liter and leave that mole on the top. So we get 0.105 still. 200 milliliters now, the same as 200 times 10 to the power minus 3, or simply 0.2, whichever. Then 0.105 divided by 0.2, you get 0.525 mole per liter in 3 sig figs. Pretty simple. But the only difference between that general concentration to the molar concentration is we're using different representations, or like a symbol to represent this molar concentration specifically. Okay, I don't mind to say like C, by the way, but C may bring some confusion because that could be many other like concentration units too. And you gotta see this from now a lot, not only in high schools, in unis, if you're studying chemistry. Oh, if you do, okay? You don't have to. Next point, question 2. Calculate the molar concentration of the solution that contained 0.24 mole of the glucose dissolved in 500 mils. Again, the way we can represent that glucose is you can show that this is showing the molar concentration. Make sure you show that relevant formula, just like N equals to M over molar mass. If you're showing you that, that's same as N over V like this. Okay, this is a requirement in the full working out. Then you're given 0.24 mole, that divided by the volume, which is 500 mils. So let's convert the units straight away, if you can do it. I mean, I'm sure you can do it. You can just convert the 500 mil into the liter, that is 0.5 straight away. Then, guys, you don't really need to use a calculator from here. 0.24 divided by 0.5 is basically 0.48 mole per liter. Question 3, calculate the amount of the moles in ammonia in 250 ml of the 0.3277 mole per liter. Okay, as we know, we learned that concentration is N over V. From here, if you want to get the number of moles, you can just change that to N is then equals to concentration times the volume. So the way we can write that answer is now the number of mole of the ammonia, NH3, is same as the concentration that you have, 0.3277, that times that 25 mils in the liter form. So 25 milliliter times 10 to the power of the minus 3 liter. Or simply 0.025. So 0.3277 times 0.025, you'd get 0.008195. This is like exact values that you have. Then shorten that into the given sig figs that you have. You're given that how many sig figs? You're given 4 and 3. So you need to follow what? The 3 sig fig value. This is then 8.219 times that 10 to the power of the 123 minus 3 mole is how we can represent in the 3 scientific figures and significant figures. Question 4, calculate the amount in moles of potassium permanganate in 100 mils of the 0.025. So it's similar methods. Question 4, we're given that to find the N of the potassium permanganate, we can use the what? C times V again. That concentration is given as 0.0250. So let's write it down all the relevant sig figs as well too. And then that times that to 100 mils. Now 100 mils, if you remember that, is equivalent to what? 0.1 liter. So you don't have to use a calculator. Just times these two, you get 0.00250. But given sig figs, 100 mil is actually the 1 sig fig. So even though we really hate to write that, this is same as 3 times 10 to the power of the 123 minus 3 mole. It's the 1 sig fig value. So what I recommend is show that exact value and then just change that to the sig fig values, just in case. Because by mistake, teachers forgot about like putting the sig figs. We do sometimes, many times actually. Okay, then you get the 1 sig fig values at the end of 2. So it's really safe to show that exact values and show the change in sig figs, and then you can argue with that. You can argue with your teacher, like, but the question says one is given 1 sig fig. We use the 1 sig fig, so I change the 1 sig fig. Okay, so let's do that. It's like a safe net for you. Any questions about these for now? Okay, let's try this one too. Now we can use the we can calculate the mass of solids that are given. So for example, in class it's at 3.3. There's some example of that. Because once we found the number of moles, from here, if I ask you to find, hey, can you convert that into the grams, which is a mass? You got to think about then the relationship is, oh, we know that N is mass over molar mass. If you want to ask, if I ask you to find the mass of that something, then N times the molar mass. Yes, time to bring out the periodic table too. Do you have one? No? Okay, get one and pass that. So for example, 3.3, we have the solution containing 6.8 milligrams of silver nitrate. It can be other way around, by the way. Whatever. Okay. Okay, let's start off from question 4 from the previous question before we move on to 3.3, please. So I'm still doing that question 4 on page 81. If I ask you to find the mass of the potassium permanganate, then from here, I can just times that N times the molar mass of it. So what you're given here is you're given. Now, in this case, do not use the sig values, use the exact value to avoid any sig error. So that'll be 0.00250. That times that, okay? That times that. Do you have a potassium permanganate? Put it in your formula sheet. You have potassium, that is 39.10 plus manganate, Mn, that's a 54.94 plus 4 of the oxygen, 4 times 16 there. Make sure you show all the relevant working out too. So 39.10 plus 54.94 plus 4 times 16. That times that 0.00250. You'll get 0.3951. This again in the 1 sig values, this is 0.4 grams. In other words, in that solution, we have 0.4 grams of the potassium permanganate in the given concentration too. So again, that's kind of a combination of what we learned in chapter 2, the mole per liter, the moles and the grams relation to the concentration as well. We can do the similar things for 3.3 on the next page, please. Now let's do this question. We have to calculate the concentration in moles per liter of the solution that contains 16.8 milligrams of silver nitrate dissolved in the 150 ml of solution there. So start off with all that relevant information you're given. So for question 1 of this, you have given mass of the silver nitrate, was it nitrate? Yeah, NO3. That is 16.8 milligrams. Just write it down, what you have. And then you need to find the volume is given as 150 milliliter. And then, once you wrote all that relevant information, do some unit conversion. That milligram is, in grams, 16.8 times 10 to the power of minus 3 grams. Volume in milliliter is equivalent to 0.150 liter 2. Okay, it's very important, like it's showing the unit conversion before you put it into, substitute it into formula. Then, from M, we can find the number of mole of the silver nitrate by N is equals to mass over molar mass. That is what? 16.8 times 10 to the power minus 3 divided by all that silver and nitrogen and oxygen. The silver is 107.9 plus nitrogen is the 14.01 plus 3 times 16 there. Then you put that in your calculator. You get 14.01 plus 3 times 16, 16.8 times 10 to the power minus 3 divided by that. You should get, oh, that's a small value, 9.888 times 10 to the power of minus 5 mole will be given. Now, save up your exact value in your calculator because we've got to use that to find the concentration of silver nitrate here. NO3. That is what? N over V like this. So put that in 9.888 times 10 to the power minus 5 divided by given volume that we found on the top, that's 0.150. So that divided by 0.150, then you should get 6.592 times 10 to the power of the minus 4 mole per liter. Now, fix that into the given sig figs value. You're given 3 sig figs and 2 sig figs. 3 from the 16.8, 2 from the 150, which means you need to convert it into 2 sig fig values, that is 6.6 times 10 to the power minus 4 mole per liter in 2 sig fig. Then this is the final answer, from the grams or milligrams into the concentration of the mole per liter. Okay, we can do the similar thing for the question 2. Let's do the question 2 as well. Oh, thank you. Calculate the concentration in mole per liter of the solution that contains 4,000 milligrams of the ethanoic acid dissolved in 100 ml. So again, write it down, all that relevant information that you have. Mass of the ethanoic acid, CH3COOH, is given as 4,000 milligram. Just simply calculate it and convert it into the grams. Isn't that just the 4 grams then? Okay, or you can just leave that in the 4 grams in 1 sig fig, that's fine. And then number of mole of the CH3COOH can be found from mass over molar mass, that is 4 divided by all the carbons and everything, so 2 times 12.01 for the carbons. We have 4 hydrogens, 4 times 1.08, plus we have a 2 oxygen, 2 times 16 like this. So, and then use your calculator, 2 times 12.01 plus 4 times 1.08 plus 2 times 16. 4 divided by that, you're to get 0.0666 mole for the given mass of the acetic acid or ethanoic acid. Then the concentration of the ethanoic acid, CH3COOH, can be found by N over V again too. So we are given 0.0666 moles on the top, or at the numerator. Your denominator, we have 100 mils. So convert that into the 0.1 liter like this. So that divided by 0.1, you should get 0.666. Given sig figs of 1, this is same as what? 0.7 mole per liter in 1 sig fig then. Okay, so it's quite straightforward once you can figure out what's given, and then from the given amount of unit, if that's a grams or milligrams, just find the number of moles and divide it by the volume. You get the concentration value quite easily. Make sense? Okay. All right. Could you try to do from this page 83, question 5, 6, 7, and 8. So 5, 6, 7, 8 only. Okay, I'll give you about 10 minutes. got your test results back. No, it's not yours. I'm just saying.
Oh, it's just an incomplete work.
Yeah. You're 12. Like, what do I do? Well, right. Started from question 5. Calculate the amount in moles of solute in each of the following solution that we have. So A, we have 0.10 liter of, you can turn that on. 0.1 liter of the 0.22 molar potassium hydroxide solutions. So, way we can do that is shorten the formulas or shorten the working out is simply write it down K or H first of all, and then you can show that CV, that is a formula of this. Then show all the substitution that we have. So we have 0.22 times that 0.1 still. Then you simply get 0.022 mole straight away. Okay. B, same method. We have to find N of the sodium iodide. It's a CV. We can use the concentration of 0.64. That times the 10 milliliter. So convert it into liter form. If you can just simply do that in your head, 10 mil is the same as 0.01 in your liter form. You can do it. Or if you're not too sure about how to convert the unit from milliliter to liter, just times 10 to the power minus 3 again. Okay, that's the best way, and not making any mistakes, but that is simply what? 0.0064. Let's check that again. 0.64 times 0.01. 0.064 mole. You may write it in there 6.4 times 10 to the power minus 3. That's the same. Okay. C. 15.6 mil of the copper sulfate. That's the CV. That again. We have 0.0150 times that 15.6. So I'll probably do 0.0156 straight away. So 0.015 times 0.0156, you should get 0.000234. Rather you're leaving these values, put that into 2.34 times 10 to the power of the minus 4, given the 3 suffix. And make sure you put the units as well too. Lastly, D, the hydrochloric acid, N of the hydrochloric acid, HCl, can be found as C, V, that again. That is 5.2 for the concentrations, 1.25 times 10 to the power minus 3. So let's write it down. Times 10 to the power minus 3 is the milliliters. If you want to convert it into a liter form, times that 10 to the power minus 3 again. So that will 10 to the power minus 6 eventually. So 5.2 times 1.5 times 10 to the power minus 6, you should get 7.8 times 10 to the power of minus 6 mole straight away. Easy. 6. Calculate the molar concentration of a 250 ml solution that contains 5.09 grams of silver nitrate. The molar concentration, so start from what you're given, mass of the silver nitrate you're given is that 5.09 gram. So in terms of number of moles, AgNO3 using the mass over molar mass. You okay, Christine?
Wait, isn't it not to the minus 3 for 5D?
5D.
Is the question, it says 10 to the power minus 3.
Oh, it's a minus 1. Sorry, I misread that. Oh, you're right. So it should be minus 1, minus 4. Sorry, it looked like a 3 in here. Angles. Then 5.2, it'll be minus 4. Yep, so it'll be why do I get the same answer? 10 to the power minus 4 then. Good. Need a new spec, okay. Alright, going back to question 6. Find the number of moles silver nitrate. Mass is 5.09. Then divided by silver, that is 107.9 plus nitrogen, 14.01 plus 3 of 16. Show all that relative working out as well. So 107.9 plus 14.01 plus 3 times 16 and 5.09 divided by that, you should get 0.029957 mole. And then get the concentration of the silver nitrate. Show all the relevant working out, that is N over V, so 0.029957. That divided by the volume, which is 250 mils, given that into 0.25 in terms of liter. So divided by 0.25, you should get 0.1198, and given sig figs of 2 and 3, fix that into 2 sig figs, this is 0.12 mole per liter then. Question 7, calculate the molar concentration of the 1.5 liter solution. Contains 1.223 grams of the, is it calcium chloride? Yes. So mass of the calcium chloride we're given 1.223 grams. Just check again. And 1.55 liters. So N of the calcium chloride from here, mass, we can use the mass of a molar mass. That's 1.223. That divided by calcium, that's at 40.08 plus 2 times 35.45. Then you should get 40.08 plus 2 times 35.45 and 1.223 divided by that, you get 0.01102 mole. That's the number of moles. Then the concentration of calcium chloride is N over V, 0.01102. That divided by the volume of the 1.55 liter. So that divided by 1.55, you get 0.0071. Now, fix that into the given sig figs. How many sig figs are we given? We have given 3 sig figs in the lowest sig fig value. So that's basically 7. It's actually 7.11 times 10 to the power minus 3 mole per liter then. Question 8. What is the molar concentration of the sodium carbonate solution prepared by dissolving 1.32 grams of the sodium carbonate in a volumetric flask that is made up to 250 ml? So that question is somewhat very similar to the practice that we're going to do today. We're going to prepare the sodium carbonate and then making it into that some standard solution today. So you're given the mass of the sodium carbonate, so mass of the sodium Na2CO3 is a 1.32 grams. Pretty much the same working out. And of the sodium carbonate is found by mass over molar mass is 1.32. Then divided by the sodium, 22.99. So 2 times 22.99 plus 12.01 plus 3 times 16 like this. Then 2 times 12.999 plus 12.01 plus 3 times 16. 1.32 divided by that, we're going to get 0.1245 mole. Given the concentration of sodium carbonate is then N over V, so 0.01245, that divided by 250 mils, equivalent to 0.250 liter. So that divided by 0.25, that's a liter and mole, and you get 0.0498. Sig figs, are we giving 3 and 2? So 250 is a 2 sig figs. Fix that into 2 sig figs. So that would be 4.98, or so 5.0 to be exact. 5.0 times 10 to the power of minus 2 mole per liter then. That's how we can write in the sig figs in a given unit as well. Pretty straightforward. Yep, I'm just kind of repeating that same procedure again and again too. All right, before we move on to the dilutions, let's have a short break, 5 minutes, okay? And then we're coming back to this, and then we're going back to the prac. All will be really upset. All right. Again, going back to this solution here. One day class told me like this looks like a urine color, so I'm like, yeah, don't make me feel that. Okay, so this is relatively like highly concentrated. So if you want to make a concentration solution again, the way I can do it is I'm simply putting another tablet here. So let's compare the colors that we have now. This is the initial color, as I'm putting there. You probably know that this is getting more darker. And the way we can find that our concentration is, it's hard to see the penetrate through that glass bottle there. When it's diluted, it's kind of more penetrate through, like you can see through, but this is getting darker and darker, almost like kind of orange juice or some soda too. So this is how we can make the concentrated solution. We simply add more solute or take the evaporate the water out. So leave that for a while. But it doesn't change the fact that we have two tablets here. So what I do is I'm going to make the full top. So have a look at the color change as we're dissolving that too. It's kind of dark orange color. As I'm putting more water there, it's getting into the more diluted colors, as you can see. Okay, a bit diluted. And despite the fact that we have the bigger like volume here, we still have two tablets. So if I can drink it, I'm still getting two tablets of the vitamin C's. So this is the main things about when we're talking about dilution again. So in terms of the number of moles, we believe that in the dilution process, we believe that the amount of the solute remains the same. This is the kind of rule that we have to use all the time. So for example, if we have the concentration one, so assume that for the, let's say for a concentrated solutions, let's write it down as C1. That's a concentration of the concentrated solution. So that is basically, I had a two tablet in the half filled bottles. Volume 1 is the volume of that concentrated solution as well too. So simply, if I ask you to find, hey, can you find me the number of moles of that concentrated solutions? The N1, which is the number of moles of the concentrated, moles of the, moles of the solute in that concentrated solutions can be found by, as we learned that N is equals to CV, that would be C1 times the C2, V2, C1 times V1 like this. In short, I can just write as C1 V1. So we got to leave that N1 is equals to C1 and V1 for first of all. You can copy that down in the explanation part given here. Okay, there's a space, you can write this one too. Now, after that, I added some extra volumes of the water to making the full tub, full like a bottles. So we call that for a diluted solution then. Then I'm gonna name that as the new symbol C2. That is a concentration of the diluted solution that we have. And the volume 2 is a volume of the diluted solution again. Then N2 is simply the moles or the amount of the solute in the diluted solution. Then where we can find the N2 is, again, we're using the formula, the N is equals to CV, so C2 times V2. In other words, N2 is equals to C2 times V2. Or the C2 and V2 like this. But remember that even though I put the extra water in that bottle there, okay, I still have two tablets. Okay, I did not change any of the solute mass. I didn't add any of the extra like in the Veroca in there. Which means that, can we say that N1 and N2, which is number of moles in your concentrated solution must be exactly same as number of moles in the diluted solution, because we didn't add any solute inside. Bring up the formula called the C1 V1 is equals to C2 and the V2 like this. Okay, where the V2 is now the final volume. So sometimes you have to read the question very carefully, especially for dilution processes, as questions sometimes giving you, hey, we added extra, or we made something into something. So let's have a look at the questions to think about like these, how to deal with those type of questions too. So remember this is C1V1 equals C2V2. It's known as dilution formula. I don't think this formula will be given on your formula sheet, but it's pretty easy to remember. It's not that complicated. So 3.4, question 1. Have a look at these questions together now. Calculate the concentration solution formed when, okay, highlight this point, when 10 mils of water is added. 10 mils now added to that 5 mils of the 1.2 mole of the hydrochloric acid. So let's write it down, all the relevant information that we have. First, we have a C1, the initial concentration that you have, or like in a concentrated solution, that is 1.2 mole per liter. That's given. We have the volume 1, that is the 5 milliliters. That's also given too. You may just use convert that into liter forms. You may do that, okay? Or I just leave that into 5.00 times 10 to the power minus 3 liter. Just leave that here like this for now. Now, we need to find the C2. That's something we don't know. Then we given the new volume. Remember that you added extra 10 mils on the top of the 5 mils. So you gotta show that the 5 plus 10 giving you 15 milliliter. That is what? 15 times 10 to the power of the minus 3 liter forms that too. Then from the dilution formula, the C1V1 equals C2V2. If you want to get the C2 from here, it would be C1V1 over V2 like this. Okay, and then show all the substitution that we have. We have given C1 1.2 times that V1 5.00 times 10 to the power minus 3. That divided by 15 times 10 to the power minus 3. Now, I want to have a look at this point in here. Yes, we converted the unit from the milliliter to the liter, which is as a liter from the standard unit we have. So, what you see that from the calculation here is we can cancel out the 10 to the power minus 3. Guess what? You don't really need to convert the unit to a liter when you're dealing with the dilution formula, because we are simply talking about the amount of the ratio factors. So I don't mind if you just put the 5 divided by 15, because at the end you get the same result anyways too, as long as they're matching units. Or if you're not too sure, just get this standard unit of the liters. You never get it wrong anyways. So 1.2 times 5, which is 6, divided by 15, you get 0.4. Again, units mole per liter. This is how we can get the diluted solution's concentration value. Let's do question 2. Calculate the concentration of this solution form when 95 mils of the water is added to the 5 mils of the 0.5 molar sulfuric acid, H2SO4. So again, let's write it down, all that information that we have, C1, V1, C2, and V2. The first concentration we have given sulfuric acid is 0.500 mole per liter. Volume is given as 5 milliliters. Concentration 2, we don't know. But remember that you added extra 95 water is added to on the top of the 5. So show that 95 is added to the 5, making the 100 milliliter like this. Again, you can change the unit of milliliter to the liters, but it doesn't really matter for the dilution factors, as we have the same unit of milliliters given. Then C2 is same as C1V1 divided by the V2. That is 0.500 times 5 divided by 100. Giving you what? 0.25 divided by 100, you get even smaller value, 0.0025 mole per liter. Yes, that. Okay, so that's not so bad. What about 3.5, question 1 and question 2? Okay, I give you a little chance, like have a think about these questions. This is not really dilutions questions, but this is somewhat like we learned about different units of the concentration and can change that into different units. So we actually need to have some concentration dilutions. Yeah. Yeah, we're going to do dilution more. Okay, let's try the 3.5 together now. Okay, so I should actually put some dilution questions rather than this, but let's finish that and then we can move on into the lab. 3.5. So what is the concentration in ppm of 0.002 mole per liter solution of sodium chloride? Remember the concentration ppm is milligrams per liter. So let's start from the given. We have given sodium chloride molar concentration is given as 0.00200 mole per liter. Just check there's a 3 sig fig values. So at the end you need to show them 3 sig figs as well. Okay, now mole per liter means that we can use as the M is equals to N times the molar mass. Yes, from the mole per liter we can change that into this concentration sodium chloride. See that I changed the unit, the representation of the concentration from the big bracket, that's the molar concentration only, to the general representation of the concentration, that is grams per liter like this. So as M equals N times molar mass, this is the same as 0.00200 times that. The grams, the molar mass of sodium, 22.99, plus that, 35.45 grams. That'll be in the grams then, in that liter form. So 0.002 times 22.99 plus 35.45 times that 0.002, you're going to get 0.11688 grams per liter there. And this is not the ppm yet, because we need to convert the grams into the milligrams to get the ppm units. So that's what. Remember that grams is a bigger unit than milligrams, so 0.11688 times that, 10 to the power of the 3 milligrams divided by the liter here like this. Then that's basically it, times 10 to the power of 3. You get 117 ppm in the 3 sig fig values. Okay, question 2. Okay, could you try the question 2? I'll give you about a minute and 2 or 2. Let's ppm it again. Okay, your answer should be 400, but 400 itself is a 1 sig fig value, so to correctly show in the 3 sig figs, show that in 4 times 4.00 times 10 to the power of 2 ppm, to correctly matching that unit, the sig picks you were given. So the rest of the working out is basically same as question 1 that we had. You know that the mass can be found by n times the molar mass. So show the relevant working out to your molar mass values, and then you get 0.39998. That gram is equivalent to 10 to the power of 3 milligrams. So that will be your final answer then. Okay, so not that complicated, and it looks like a really straightforward for those calculation processes too. So next week I'm gonna bring some more questions, and that's going to use a bit of like stoichiometric questions as well too. In other words, you get some reactions and then get some calculation, and you get the limiting reagent again too from it. Okay. All right, that's all for the contents for today, and let's move into the lab. We're gonna make some standard solution today.